There is a big complex engineering problem in the global solar industry today. Conventional monitoring systems often raise false alarms because of transient weather such as passing clouds. This leads to huge operational expenditure on unnecessary manual inspections, while early stage anomalies are often missed until permanent damages occur. My project is created to solve this problem. My name is Aaron Benjamin Danker, an engineering undergraduate from the Department of Electrical and Electronics Engineering at Universiti Teknologi PETRONAS. My project is titled an AI-enhanced health monitoring system for photovoltaic arrays. For this purpose, I designed a decentralized edge computing architecture built with just an ESP32. To feed the AI system, I created a custom multi-dimensional sensor array that captures a complete profile of health of the solar panel. Real-time voltage generation is monitored by using an ENA219 sensor for the electrical data, while for the thermal data, I implemented the usage of a BME 280 ambient sensor and a DHT22 sensor to obtain the ambient temperature and humidity of the environment. While for the temperature of the solar panel, I used an MLX 90614 infrared sensor. This specific sensor was chosen as an accurate and cheap alternative to the expensive thermal cameras to allow the system to detect localized hotspots on the panel surface. Finally, the usage of a piezoelectric sensor was integrated in the system to check structural integrity. It captures raw vibration spikes, allowing the AI to identify physical stresses such as heavy wind impacts, debris strike, or loose mounting hardware. All this telemetry gets packaged up and sent over Wi-Fi every 5,000 milliseconds to a local server. The data is processed at the location by a 5-class XGBoost machine learning model, which has been shown to classify the array state as healthy, hotspots, vibration stress, shaded, or overcast or raining. This model has a 99.66% accuracy. But the real innovation of this system is the environmental debouncing logic. To avoid false alarms, the system requires a 60 count continuity threshold. 5,000 milliseconds times 60 readings provide a tight 5-minute validation buffer. The dashboard illustrates how the system can disregard transient weather phenomena such as passing clouds and only trigger actionable maintenance alerts and telegram notifications as soon as permanent physical faults are confirmed. Here is the live dashboard in action. Under normal conditions, the AI classifies the array as healthy. But when the infrared sensor detects localized heating and the 5-minute debouncing filter confirms it is not a passing cloud, the system instantly triggers a critical hotspot warning. Scrolling down to the analytics, it can be clearly seen that the sudden spike in panel surface temperature on the live telemetry graph. Simultaneously, the system updates the maintenance log, generating a specific prescription to inspect the affected module to ensure the operator never misses a critical anomaly. This actionable prescription is pushed via an API to a Telegram bot. This delivers a real-time alert directly to the user's phone, transforming reactive checks into immediate predictive maintenance. We need to do more than just build more solar farms to achieve SDG 7, affordable and clean energy. We also need to optimize how we maintain them. My system is a catalyst to convert solar maintenance from a reactive, labor-intensive activity into an anonymous predictive system. This system uses edge computing to proactively remove false alarms and detect early-stage anomalies, preventing permanent module degradation. When scaled out across commercial solar farms, this technology significantly reduces operational costs, prolongs the life of millions of solar assets to prevent global e-waste, and accelerates our transition into a resilient, intelligent, clean energy infrastructure per SDG 9. Global change doesn't always come from inventing the next big thing. It comes from engineering smarter ways to preserve what we have already built. Thank you.